Welcome to all in this lecture. This is the second lecture in the series of basic mechanical engineering. In this lecture, we are going to study the Carnot cycle. So let's start. So what does the word isentropic process means? Isentropic process is a necessary concept for understanding of the Carnot cycle. So let's start. Isentropic process, as the word suggests, it is a constant entropy process that during the process the entropy or the randomness of the system remains constant, doesn't increase or decrease. All isentropic processes are reversible and adiabatic. So what does the reversible process means? Reversible is a process in which the system is at equilibrium at each and every step. It is called as the reversible process and adiabatic. For example, if the hot tea is poured in a thermos, the energy is not transferred from surroundings to inside or from inside to the surroundings. It is called as the adiabatic process. All isentropic processes are reversible and adiabatic in nature, but vice versa is not true, means that all the reversible and adiabatic processes are not isentropic, that is no, vice versa is not true. So what does the Carnot cycle says? Carnot cycle is a theoretical ideal thermodynamic cycle, that it is a ideal cycle and practically impossible. Why it is impossible we will see in the further slides. It was proposed by a French physicist, Sadi Carnot. It provides an upper limit of efficiency that a classic thermodynamic engine can achieve during the conversion of heat into work. What does the sentence means? That it gives the upper limit, that it is gives the highest efficiency that any engine can achieve while converting the heat into work. That it gives the maximum efficiency. It gives maximum efficiency. The simple meaning is that. It is a theoretical construct and practically impossible. This is the graph for the Carnot cycle, plot for entropy versus temperature. This is the temperature graph. This is the highest temperature. This is the coldest temperature. Okay. It is in clockwise nature. All the power producing cycles are clockwise. All the power producing cycles are clockwise. And if we see for heat pumps, the cycles are anti-clockwise. Okay. So let's see from 1 to 2. Okay, from 1 to 2 the entropy is constant. So what does we say? It is isentropic. What does the word isentropic means? Isentropic also says that it is adiabatic. It is adiabatic and also it is reversible. Reversible, okay. And the entropy is constant, but the temperature is increasing. Temperature increasing and entropy constant, so it must be compression. Okay, see here, 1 to 2 is the isentropic adiabatic reversible compression. Okay, so now see here, from 2 to 3 the temperature is constant. The temperature is constant, so it is isothermal it is. Okay, now see, the entropy is increasing. So what does entropy increase means? When does entropy increase? Entropy increases when heat is added. So it is heat addition, isothermal heat addition. Okay, and when heat is added and entropy is also increasing. So what does it mean? It is expanding. The gas is expanding. It is expansion. Okay, see here, from 2 to 3 it is isothermal heat addition expansion. Okay, now see here, from 3 to 4, what does we see? From 3 to 4 the entropy is again constant, so we will say it is isentropic. It is isentropic. Okay, and now isentropic means adiabatic and reversible, we know that. But now the temperature is decreasing. The temperature is decreasing at a constant entropy. At a constant entropy, so it is expansion. And when the gas expand, what does it mean? When the gas expand at a isentropic process, It means the power is produced in this cycle. Power is produced in this cycle. From 3 to 4, from the step 3 to 4, the power is obtained from the engine or from the Carnot cycle. From 3 to 4, the power is obtained. See here, 3 to 4, isentropic, adiabatic, reversible, expansion and power stroke. We can also write it as power stroke or power produced in this cycle at 3 to 4. Okay, now see here, the last step is from 4 to 1. 4 to 1, the entropy is decreasing, temperature is constant. Temperature is constant, so isothermal. Okay, isothermal, temperature is constant, so it is compression. Entropy is decreasing, temperature is constant, so it is compression. And heat is rejected here, means the heat which is not used, it goes to the low temperature reservoir. Okay, low temperature reservoir, it goes from 4 to 1. Okay, now we understood. See here, 4 to 1 is isothermal heat rejection or also known as the compression. So we understood the processes involved in the Carnot cycle. Now let's have a study of the drawbacks of the Carnot cycle. We know that it is an ideal cycle and practically it is not possible. Practically not possible. So why it is not possible? We have to see that it is a theoretical cycle and practically impossible. Heat cannot be added to a system at a constant temperature isothermally. So what does this statement means? Have a look at here. We know that from 2 to 3, the temperature is constant. Temperature is constant. So it is called at isothermal. But heat is added. Heat is added. But when to a system we are adding heat, when we are adding heat to a system, the temperature will surely increase. Temperature will surely increase. But here it is given that temperature is constant. It is impossible to add heat at a constant temperature. Temperature will surely rise. So it is a drawback of Carnot cycle. It is impossible practically to add heat at a constant temperature. So it is a drawback of Carnot system. Okay. Now from 3 to 4, see here, from 3 to 4, 3 to 4 the power is produced. 3 to 4 power is produced, but the entropy is constant. When entropy is constant, power cannot be produced. When entropy increases, power is produced. When entropy increases, power is produced. So it is again impossible for the obtaining power at a constant entropy. So again it is the drawback of the Carnot system. Okay. And last point, heat cannot be isothermally rejected. So what does the statement mean? See here, from 4 to 1, heat is rejected at again at constant temperature. Constant temperature. When a system is rejecting heat, its temperature should decrease. But here it is given that heat is rejected at a constant temperature. So again it is a flaw. It is practically impossible. Hence, Carnot cycle Carnot cycle is the ideal cycle and practically impossible. See, practically impossible. Okay. It is now, this is the volume versus pressure diagram of the Carnot cycle. This is the T1 temperature, T2 temperature. Here again the same 1 to 2, 2 to 3, 3 to 4, 4 to 1, and this graph is also clockwise. All power producing cycles, any graph is clockwise in nature. Clockwise in nature. Okay. So we will stop here. In the next video we are going to start the air standard cycles. Thank you.